Right. So today we'll talk about modular arithmetic and binary exponentiation. So you might be thinking, why is modular arithmetic in dynamic programming one, right? So all the DP counting problems, right? You can never solve it without knowing modular arithmetic, right? And modular arithmetic in itself is such a vast thing, right? That it requires to be a different topic. I cannot just talk about it in DP and leave it off. It's really big, right? Not too big. We can cover it in this single class actually. But again, there are few things that I'll just tell you. Okay, and to understand the entire proof, now understand modular arithmetic is maths. It's not even computer science. It's pretty hard maths. And modular arithmetic is something that we don't learn in school, right? We learn addition, subtraction, multiplication, division, but no modulo, right? Even though it's just like a mathematical operation, right? So there are things like if like actually if you go to China, like people do learn modular arithmetic in school itself, right? So it's nothing new for them, but for us we have to learn it separately, right? And even before, so basically for counting DPs you need modular arithmetic, right? And for basically for modular arithmetic you need binary exponentiation, right? So that's the order that I'll teach you, right? So I'll start with binary power right now. It's called binary power, binary exponentiation, and a lot of different stuffs, but everything corresponds to the same thing, right? So we'll start with binary exponentiation, right? So what is binary exponentiation? Binary exponentiation is actually a really smart thing. It is also used in something called matrix exponentiation. I'll tell you what matrix exponentiation is. It's really very fascinating. Matrix exponentiation. It solves very hard problems. Okay, but I won't be teaching that. You won't require that for placements, right? So what binary exponentiation is, that say you're trying to compute this 2 raised to the power 16, right? I'm starting with a really easy example so that you understand, right? Now what if I tell you, instead of computing this, like can you do it something like this, and maybe compute 4 raised to the power 8, right? Instead of this, why don't you compute this, right? So and again, instead of this, why are you not computing this? Instead of this, why are you not computing uh, something 16 square? What's 16 square? 256. So instead of this, why are you not computing 256 square? And basically you can just compute this, right? Now if you brute force, how many steps is this going to take? This is going to take 16 steps, right? But did you just realize I just did it in 1, 2, 3 and 4 steps, right? And if you can match it, you can see that actually log 2 of 16 is 4, right? So this is why it's called binary exponentiation, right? You are doing the exponentiation, but you are doing it in, say, in a binary manner, right? More like I am, like every time, like if I had to do this, let's say 2, I have to do raised to the power 4. So instead of doing this into this into this into this, I know that I can just do this, and I can just do a square here. I don't need to do this again, right? This is redundant. Now same goes if you can capitalize again, right? If there was something like this, like I'm basically explaining this in a figurative manner, right? You squared this, you remove the redundant operation here, and you can again capitalize on this, right? You can do 2 into 2 square and remove the latter part and square and again capitalize on this. So do you realize how I'm compressing the exponentiation, right? So this is basically binary exponentiation, right? I hope you get the intuition, right? And now I'll explain you what happens for some corner cases. So the steps minimizes to square root of n for, or no, it's not square root of n, Harish. Minimize to square root for all x raised to the power. It's not square root of n, it's log. Right. Realize that what, okay, I'll explain why it is log. So for 2 raised to the power x, the next thing that you're trying to compute is, let's not take something specific. Let's take a raised to the power x. The next thing that you are trying to compute is a into a raised to the power x by 2. Something similar, right? Take this example. 2 raised to the power 16, the next thing you are trying to compute is 4 raised to the power 8, right? And the next thing that you will try to compute is a raised to the power 4, and this will become x by 4, right? This goes on. This becomes a raised to the power 8, and this becomes x by 8, which actually, if you open the brackets, right, if you actually open the brackets, the power is in in multiplication, right? This is actually a raised to the power x, but you are breaking it down, right? You are computing the power in steps of 2. Instead of a raised to the power x, you are multiplying a and you are doing x by 2. Then you are multiplying this whole thing with itself, making it a raised to the power 4, and you are decreasing the power by 4 times, right? So x was supposed to be the original step, but can you see that it's decreasing by 2 times every single time? X by 4, x by 8, right? And one point it will become 1, right? Now for people who don't know, okay, this is something that I've talked about a lot of times earlier in past 2 months. So the number of steps required for a number to reach 1 by constantly dividing it by 2 is actually logarithm, log to base 2 for the same number, right? You can try, you can instead of proving mathematically, just try. 16, 8, 4, 2, 1, right? Basically it's log 2 of 16, right? It's 44, I know, so it's like 1, 2, 3, 4, like 4 steps, right? So this is called binary power, this for the same reason. And why is it binary? You are dividing the whole step by 2 every single time. X was supposed to be the original number step, now it became x by 2, now it became x by 4, now it became x by 8. Similarly, it reaches 1 at one point, and that is where we stop, right? A raised to the power x, yep. A raised to the power n by x by exactly. So uh, I know a lot of you might have already seen this, right? So for people who have not, please do not hesitate to ask. I might speed a few things up, thinking that you already know that, but I know there are a lot of new people as well who have joined, and I'm not really sure how much you know. So please ask, right? There's a raise hand feature. You can use that, right? Sometimes you can just open your mic and speak as well, because it won't be possible for me to monitor whether you're raising a hand or not. If I get the notification, it's completely fine. I'll immediately see that. Otherwise, please, you can just open your mic, right? I don't mind. You just open a mic in between, right? So, so there's one thing. Now, you'll say, how about something like a raised to the power 7, right? You cannot do a raised to the power 2.3, right? Basically, right? You cannot do it by 2 because this is 7, and you basically are doing a floor division, right? So for numbers like these, you just change it to something like this first, right? So you take one additional step, you change it to something like this, right? And then you continue doing it, right? Now again, to calculate this, you change into, sorry, a square into a square of square, right? And then you do a of a square, and basically this is a4, right? Now actually, if you look carefully, you'll see binary every single place, right? If you see 7, this, the sum of powers, right, is actually 7, right? Or let's take some other example, like for something like 17, right? For 17, again you do the same thing, you do a dot a16, right? And then you start breaking this down, right? Now how you do it is, algorithm wise, how you do it is, you maintain a variable called res, which is actually equal to 1 first, right? And every time the power is odd, okay, every time the power is odd, you multiply what is your currently a to this res, right? So basically, if it was 17, res becomes a, and you can basically remove a from here, and you can keep doing this again, right? For some different number, let's say 11, you write it as a dot, you write it as a raised to the power 10, you put res as a, right? You write it as a square raised to the power 5, right? A square raised to the power 5, and again, if you see that 5 is odd number, so you split it into, you don't split it, what you do is you pick this and you multiply it here, so a dot a square, you write it like this, and you remove one power from here, so it becomes a squares 4, right? You remove one power. Now again, 4 is even, so it's not a problem. So you write a raised to the power 4 square. It's again even, that's not a problem. So you write a raised to the power 8 1. Now 1 is odd, so you write this here, right? Or did I do some mistake? 8242. Yeah, this is correct, sorry. Right. So do you realize that every time the power becomes odd, right? Every time the power becomes odd. So basically what is happening is a is squaring itself every single time, right? And the exponent is dividing itself every single time, right? So I hope you are able to understand how powers are being transferred, right? And if you see, in just 3 steps you have computed it, right? Now 3 steps actually. Res just takes 3 steps. We didn't store res here. Now this is guaranteed that res will contain everything, because in the end it is going to be 1 anyway, right? 2 is going to be 1, and this is what your answer will look like in the end, and it will get accumulated anyway in res, right? So I'll just write the algorithm if it's a bit confusing to you, right? So bin pow of a raised to the power b, okay, we take ab now instead of x. So you put res as 1, and while b is not equal to 0, right, what you do is, if a sorry, if b modulo 1 b modulo 2 is 1, basically if b is odd, what you do is res is equals to res into a, right? If it's not, nothing happens. You multiply a, you divide b, right? Then in the end you just return res.
It
Someone
should be
trying to
b
speak
not
something?
equal to 1, right?
Sorry?
It should be while b is not equal to 1, right? Or
No,
greater than
it should
0.
be not equal to 0, because if b becomes 1, right, you remember this last step, you need this to get accumulated in res, right?
Right.
So
But then
that only
b will.
sorry.
Oh yeah, b can go below 0. Okay, okay, yeah, yeah.
Yes,
Never mind,
yes,
never mind.
yes. See what happens is, in last step, in algorithmic, what happened in last step, this accumulates to res, and a actually becomes a raised to the power 16, right? Because of this, right? But you realize that you break out of the loop, and this never gets accumulated. You just get accumulated, a raised to the power 8 gets accumulated in res, right? And this
Right.
actually corresponds to 11, right? So this is all actually the check condition as well as base condition. It's really smart. B modulo 2 is equals to 1. How is it the base condition? Because in the end it's going to be 1 anyway, so you have to accumulate it into the answer. How is it a check condition? Every time it's odd, you cannot do a modulo 2. Sorry, you cannot do a by 2, because you will be losing something. So you add a part of it in the answer, right? So this this is actually bin point. It's pretty simple, right? And it just takes logarithm of b time, right? At the same time, it's very powerful. Remember that all the power operation or power function that you use is not, at least in C++, it's not bin power. Okay, it's not binary power. It's normal power. So at places where you want a very high exponent, you cannot use that, right? And again, if you don't have doubt, I'll quickly shift now, because this is an easier topic, right? Now, why I need bin power, right? Now, to understand why I need bin power, let's dive into modular arithmetic. Okay, modular arithmetic requires bin power very extensively, right? And you'll understand why. So we'll start with modular arithmetic. We'll come across bin power. So modular arithmetic is actually pretty simple thing, right? Like at least with on the face of it, on the surface, it's pretty simple. So we say that a plus b modulo m can be written as a modulo b, sorry, a modulo m plus b modulo m, and you do a whole modulo, right? Right. And again, like this is something pretty simple. You do not, if you want something like a proof, so a can be written as something like b dot m plus c, uh, can be written as x dot m plus y, or x1 dot m. B can be written as x2 dot m plus y, right, as some multiple of m and a remainder y, right. Any number can be written in the form of this, right, as long as actually any number can be written, x1 can be 0, right. So if you want to write, if a is like 15 and m is 7, you can just write 2 dot 7 plus 1, right. Now when you add both of these, you get x1 plus x2, right, times m plus y1 plus y2, right. And you do a complete modulo, what you get is this becomes 0, modulo m, this becomes 0, and what you get is this modulo m, right. Right, if you do a plus b modulo m, right. But if you do it individually, so what will a modulo m look like individually? It will just look like y1, right, because this will get become 0, and here it will look like y2. So a modulo m plus b modulo m will be basically y1 plus y2, and then again you do a modulo m. So basically both of them are similar, right. Basically if you add them first, this the exponents will get added, and if you, when you modulo, it will become 0. If you don't do that, they will become 0 individually. So this is how the this theorem holds, right. But why is this important? This is important because integers have a fixed range, right. They have a fixed constraint, like the range of values that you can store, right. So in C++, you can just store 2 raised to the power 31, right, signed. In a signed integer, you can just store 2 raised to the power 31. So if a and b both were 2 raised to the power 31, 2 raised to the power 31, and say m was something 2 raised to the power 29, right. So adding this will give you an overflow error, right. So that is why you need to modulo them separately, right. So when you modulo them separately, this a becomes less than 2 raised to the power 29, b becomes less than 2 raised to the power 29. Then adding them won't give you a out of range error for the data type, right. I hope this is understood, right. So adding this will give you will put the sum out of the integers range, right, because adding this will give you basically 2 raised to the power 32, which is greater than 2 raised to the power 31, the range for signed integer in C++, right. So you'll get integer overflow error, right. So you modulo them individually, then you add it, right. Now I hope everybody understands that when you modulo some number modulo m, the result is going to be between 0 to m minus 1, right. Yeah, so this again very exactly similar thing hold with a minus b. Actually a minus b is basically a plus minus b, right. So you don't need to prove that again a into b. Now a into b is something more complicated, right, because a for a into b, doing just a modulo m into b modulo m is not enough, to be honest, right, because something like this can happen, right. Now again, people using python don't need to worry about it, right, at this stage right now. So if this is something like 2 raised to the power 20 plus let's say it's again a into b, and both a b are in the range of say 2 raised to the power 20, and the modulo m is in the range 2 raised to the power 29, like we did earlier. Now what happens is a modulo m will again give 2 raised to the power 20, right, because this is already smaller, right, but multiplying them will give 2 raised to the power 40, which is greater than the integer range, right. So basically in C++ you have to do, in Python you don't have to do this because there is nothing called a range, right. But again, you cannot store infinitely large numbers like 2 raised to the power 200. You can store it, but again the operations that you do will be so huge that you'll run out of time, right, if you do operations on such numbers. I think there was some modulo question in your test, and I think in Python, like people basically using Python, you don't have a habit of like tracking the size of the or the range of the number that you're storing in an integer. So if that becomes really huge, even if you're doing some simple arithmetic operations, it will take a long time, right? Because once it surpasses what 64 bits, you are storing it in a list now instead of single integer. Remember that. Then the time complexity is basically equal to the time complexity of the list now. If you have 100 2 raised to the power 100 digit, something like this, or say 100 digits, right? So you are taking O of 100 every time you are doing an operation, like something like that, right? So remember that, right? Okay, so back to the same problem. Now, to solve this thing, what you have to do is you have to push it to a larger data type first. So in C++, how you do it is you do something like this: A into LL into B. Now, what is LL? LL is long data type, right? Again, Python people don't need to worry, but still understand what are like integer constraints, right, or data type constraints in general, right? So that's processed you to long data type which has a storage of 2 raised to the power 64, which can actually hold this value. So to handle this, you can never handle it by A modulo M into B modulo M, right? Certain cases I'm talking about, right? Again, if this uh, like even if you do this, okay, let's take a new page first. Right. Like even if you do this, you'll get something like 2 raised to the power 29. Right? Even if A and B were in range greater than 2 raised to the power 29, you're going to get 2 raised to the power 29 to 2 raised to the power 29. Just won't handle it. So basically, you send this to a higher data type, right? So you multiply it, you explicitly typecast it to a higher data type, making the range of the integer no data type into 2 raised to the power 64. Basically, 63 for sign, right? And this can then be handled, right? Because actually 2 raised to the power. Yeah, this can then be handled, right? This will reach what, 2 raised to the power 58, right? Which is less than the constraint, right? So this won't overflow, and when you do a modulo, it will take care of that, right? So again, basic things for A plus B, it's easy. You just do A modulo M plus B modulo M and hold modulo M, right? And for A into B, basically you have to typecast it, right? So again, if you are having a modulo inside or not, it doesn't matter a lot, right? So even if you don't have it here, it's fine. So it becomes A into 1 LL into B modulo M, right? And for minus, you can just use this. Just one thing about minus is that, can somebody tell me what is minus 5 modulo 7? Yeah.
5, or it should be 5, right?
No, it's not 5. You add it. No. You
Ah,
have to add it. It's 2. Yes. How is it 2? Is that what doesn't change in modulo is like x and y can be same under modulo when y is equal to some x plus k times m, right? Because when you modulo it, basically this becomes 0, right? So you can add any amount of that number, that modulo, and the number will still remain the same. So in minus 5, you can just add m, basically minus 5 plus 7, and it becomes 2, which is same, right? So basically you can say that 2 under modulo 7 is actually equal to minus 5 under modulo 7, right? So every time you have a negative number, remember to handle this as well. All right. Now we come to something more interesting, right? I actually took a session last year. It has been more than a year, and I took a session on modular arithmetic. I think it was in smart class. I think Ishwara was there. Yeah. So this is very interesting, and it's called modulo inverse. Okay. Now it makes actually no sense for an inverse to exist in modulo, because every time we talk about modulo, right? Give me 1 second. I'll just give my attendance. Yep. Thank you. Yeah. So in modulo, we never talk about fractions. Okay, this is one thing that you have to remember. Modulo is always done on absolute numbers, right? Absolute values. You see this, absolute values, right? We never talk about decimals, right? But the fact that a division, right, might produce a double, and we can never. Can you find this something like this 2 or something like 17 7.8 modulo 7. There is no answer to this. Like, it doesn't even make sense mathematically. Right, okay, you can give something like, okay, the remainder is 0.8. But we never talk about modulo in decimal sense, right? So this, it makes no sense to even compare something like this. But actually, an answer to this exists. Right. Now, to find how this exists and why is this important, no, why is this important is that when you're calculating, when you're doing some counting DP, right? So you will have to do something like a by something, right? Let's say you're using this formula, right, for counting DP. You have to do a by 2, right? Now they say that count the number of what configurations modulo some number 10 raised to the power 9 plus 7, let's say, right? Now you'll say that a division operator is not valid. How am I supposed to do this? Actually, they have it. They say that for numbers like p modulo q, please report the answer into p modulo q inverse. Now, how do you find the inverse? Right. This is what is called a modulo inverse. Right. Now, let's break everything down. Right. Now, please pay more attention from here because this is actually really hard. Right. Now, what modulo inverse is that? Now tell me, what is an inverse for a simple number? Now this will look very stupid, right? This is an inverse, right? A very general meaning of inverse. For a, this is a inverse. What is actually a inverse? Nothing but 1 by a, right? Right. But do you understand that this b here might not, like under modulo, right? If this gives 1, now there is some form of expressing modular arithmetic. It looks like this. So don't be afraid if you look, if you find this somewhere. It just says that both the sides are modulo m. Okay, this is equivalent, right? It is equivalent to 1 modulo m. So basically, it just says that a dot b modulo m is basically 1 modulo m. That's all. This is a concise way of representing it, right? Now, can you understand that this b here is not necessarily 1 by a, because first of all 1 by a doesn't even exist in modulo theorems, right? So
As
yeah,
A dot B as in A into B or A modulo B? It's A.
sorry, it's a into not modulo, it's multiplication,
Oh, okay,
right?
okay.
Exactly like here, right? So a into b. Okay, so here, and y, can it be a different number? As I told you, right, under modulo y can be equal to x, right? Y can be equal to x modulo m, right? Like this can be equal when x, when y is something like, say, let's say y is something k dot m plus x, right? And let's say x is less than m, let's just say. So under the mods, both the numbers will be equal, right? Let's say 15 and m is 7 and 8, right? Now both the numbers are different, right? 15 is a different number, 8 is a different number, but actually under mods both of them give 1, right? So what I'm trying to say is here b is not necessarily 1 by a, right? B can be a very different number, but the general thing that you want to know about b is when you multiply a and b and do a modulo operation, you should get a 1, right? Let's take one very simple example to understand it. M is 7 and a is 2, right? Now you have to find a number such that when you multiply it by that number, you get a 1 under the mods.
4.
Sorry.
4.
Yep, b is 4. Yes, so 8 modulo 7 is 1. Now tell me, do you understand that b is called the modulo inverse, or the modulo inverse of 2, or more formally 2 minus 1 is, or no, it's not like this. Basically 2 dot b, or yeah, you can actually write like this as well. If you send 2 here, you will realize that b is 2 modulo inverse, right, which is basically 4, right? Now do you understand how you are calculating this? right? You're basically, again, I'll say this whole thing again. For any number a, find a number x such that when you multiply the number by x, you get 1 under the mods, right? So if this holds, x is a modulo inverse of a, and a is a modulo inverse of x as well. It's both ways, right? Any doubts until here?
The value of, let's say, a.
Yeah,
So if I want to find a's inverse, the value of a's inverse is depend on n, right? It's not
on
a
m, yes.
right. Okay, good. That's what I wanted to
Yes,
clarify.
yes, yes. It depends. Now we'll see how it depends actually. Now let's find. Okay, how do you find the inverse? Now there is a brute force way, right? And brute force way is pretty simple. You might have guessed as well. You find take all the numbers from 1 to m. The number can also be its own inverse. Okay, it's not necessary that x is a different number, right? It can be that a square is 1 mod m. It's entirely possible, right? Take some number, 5. What is 5 square? 25. Right,
24.
25. Let's, yeah, take 24. So 5 square, yeah, 5.5 is 1 mod 24, right? So you take 1 to m, and for every number you check what is a dot, let's call this x. What is a dot x modulo m? As soon as you get 1, you realize that x is the a inverse, right? It's the modulo inverse of a, right? This is brute force. It takes O of m time, right? Which you might have also guessed is not feasible, because basically in some counting problems you might have come across some counting problems, right? I have give 1 or 2 counting problems as far as I know, very easy ones though, right? M is as large as 10 raised to the power 9 plus 7, and anything greater than 10 raised to the power 7 is going to give you a time limit exceeded, because basically the current compilers take 1 second to compute something like this, right? So O of m is not possible, right? You have to come up with something more powerful, right? Now, mm, there's some maths behind it, and I explained it in last month when I was teaching GCD. Okay, now even for people who were not in that class in that month, it's not like it's something standard. How many of you have heard about this? It's called linear dope. Even I cannot pronounce it. It's linear Diophantine equation of two variables. It is extended Euclidean algorithm. Basically, what it says is, given any number a and b, you can always find an equation that corresponds to this. So, if I had to take an example, uh, 5, 7. So, x dot 5 plus y dot 7 should be equal to the GCD, which is 1, right? Okay, dot is multiplication. Okay, please don't confuse it with something else, right? So extended Euclidean theorem says that there will be a solution to this, right? And in fact, if you try, you can find a solution to this, right? Let me see if I can find it really quickly. So 5, 10, 15. Actually, yes, 3.5 plus minus 2.7 is 1, right? 15 minus 14 is 1, right? So this is extended Euclidean algorithm, and with this you can actually find modulo inverse. And how? And it's really smart, right? See, again, we are trying to find ax is equivalent to 1 mod m, right? Now we'll take, now the only condition, okay, for a modulo inverse to exist is that GCD of a and m should be 1, and this can actually be proved by extended Euclidean algorithm, right? That's one proof. The other proof, you can try it yourself. Like if a is 2 and m is 6, you're never going to find a you'll never find an inverse for a. You can try 2, 2.1, 2.2 is 4, and you can keep on going. 6, 1, 2, 3, 4, 5. You can just go till 5, right? So you can 0 makes no sense, right? So 8 and 10, right? Modulo will give 220, sorry, 24024, right? You're not getting a 1 any time, right? So the only condition for modulo inverse to exist is the GCD of the number that you're trying to find the modulo inverse and the mod under which you're trying to find the modulo inverse should be 1, right? And you can see here that you require that here, right? Now I'm quickly going to tell you how you can use the extended Euclidean algorithm. You don't have to code it, okay? I'll tell you a really simpler method as well, right? That will always work. This is just for your information. If nothing works, okay, actually if nothing works, I think I've seen a question where m was actually equal to 10 raised to the power less than 10 raised to the power 6, okay, and you can actually brute force it, right? You just had to find the modulo inverse. That was a complete question, right? But there was one constraint that existed that I'll let you know, right? So let's quickly talk about extended Euclidean algorithm. So you take a and m and you write x dot a plus y dot m is equals to 1. Do you agree that a solution will exist? Because I just told you, right? Based on extended Euclidean algorithm, a solution will exist for this, right? Now do a modulo m on both sides. What you'll get is x dot a, this will become 0, and this will be 1 mod m, right? Exactly what you wanted, exactly what I wrote here, right? So whatever your coefficient of x is here is actually the inverse of a. Take a minute, look at this again. How you write this is extended Euclidean algorithm. You don't need to learn it. I'll tell you a simpler way, right? But again, there are actually, if you go to CP Algo website, there is a complete function that can help you find it, right? And it's some mathematics. People who have studied cybersecurity might have studied this as well, right? I have studied it, how to find modulo inverse using extended Euclidean algorithm, right? But again, you don't need to do this, but understand how I wrote this. I'll go over it again. So what extended Euclidean algorithm tells you is it's called linear Diophantine equation, right? And what it says is that you can write some combination of a and whatever other number that you have whose let's say you're trying to find a GCD, or you have found the GCD, so you can write any number a and b in such form x and y will exist, like the solution to this will exist. So I just wrote it. I took a as a, I wanted to find a inverse. I took b as m, under whose mod I have to find a inverse. Once I wrote this equation and I solved this equation, now there will always be a solution. Extended Euclidean algorithm guarantees that once you solve this equation and you find x, you modulo both sides by m and you're going to get this exactly. And remember, you found x, right? That x is a inverse, right? So this is one way. Another way of finding this, an extended Euclidean algorithm takes logarithmic time. So this takes O of, again, log 2 of it should take m, right? The complexity is actually similar to Euclidean's GCD theorem, and why m and why not a, because this is actually maximum of a and m, right? And which is always going to be m either way, right? Actually, even if it's a, you just do a, you get a mod m, and it again goes back to m, right? Anyway, that's something else, but it will do it in logarithmic time, right? So we came across two approaches. One takes O of m, other just brought it down to logarithmic of that, right? Now we'll see the third way, and this uses Fermat's Little theorem, right? Fermat, I think it's Fermat Little's theorem, right? And again, I'm not going to prove the theorem, okay? There's a whole research paper if you want to read, right? So what the theorem says is that a raised to the power some prime number, right? Remember, here it's prime, there it was co-prime, right? GCD of two numbers are 1, both the numbers are called co-prime. You want to say something? Cool. So this is what Fermat's little theorem tells us. Right. Now understand, P should be prime. Right. Now, once P is prime, a prime number is always co-prime with any other number, right? So you don't have to worry about anything else now. Right. Now, see what I'm going to do. I'm going to divide both the sides by a square. Right. So what is going to happen? AP minus 2 is going to be equal to A inverse mod P. Right. Now you found another way to find A inverse, right? It's basically A raised to the power P minus 2. Right. Or writing in familiar terms, A raised to the power M minus 2 is basically A inverse under the same mod, right? M. Remember, M. Right. And this is the easiest way that you'll get actually to calculate this.
Manas, can you just show the previous page once?
Yes. Take a minute. Ask your doubts.
Cool, cool. Understood.
Cool. So again, A inverse, calculating A inverse just requires you to calculate A raised to the power M minus 2. Right. But again, this power can be huge, right? What did I tell you? M is most of the time something similar to this, or in most of the questions, what the mod that you're going to get, right, unless it is a very specific question, will be either the first prime number that's greater than 10 raised to the power 9, or the first prime number that's less than 10 raised to the power 9. And I'm pretty sure you might have seen two combinations. One is this, and the other is some 998 or something. I don't remember exactly. Right. So these are these actually. Right. Now again, the problem is you can, like, M is really big, right? If you compute the power with brute force, it will take OM time. But right now we started with discussing binary power, right? So calculating this is going to take O of log M of time, right? Again, right? So again, you can calculate the inverse of a number in logarithmic M time, which by just calculating this, right? So if I tell you now to solve, to tell me what is P by Q modulo M, what you are going to tell me is P dot Q inverse modulo M, which is basically P dot Q raised to the power M minus 2 modulo M, which you have to calculate it like P into 1 LL into Q raised to the power M minus 2 whole modulo M, provided this function also returns a modulo M, which we'll discuss in next 5 minutes. Tell me, do you understand this page? This page is what I have been teaching for the entirety of today's class. Tell me if you have doubts in this page. So anytime you come across a question, this is what you will be asked. When you have to report P by Q modulo M, this is what you will have to report. Right? So I'll again write this. I'm changing the page. I'll again write this. P by Q modulo M, you basically have to report. For Python people, it's fine. You don't have to do that into 1LL thing. Right? But in C++, you'll have to take care of that. Right? Q raised to the power M minus 2 modulo M. Remember this, right? Now we'll write, is there anything else left in modulo arithmetic? Now we'll write binary power again, right? And I think few of you got the question to calculate the combination, right? Some NCR, which I'll tell you how to do it efficiently using modulo arithmetic under mods, provided it was under the mods. Right, I'll tell you how to do it efficiently. Right. Now, please, if you have any doubts right now, ask me, because later it will get even harder. if you don't understand this, right?
Could you scroll back to 2 pages before, where you first divided uh, the entire equation by a itself?
By a square, this.
Yeah, it's correct. Sorry, yeah.
Yeah.
So over here on the right hand side, we have a power minus one, right? But
Yes.
a power minus one indicates the multiplicative inverse, right? It's not the mod inverse. I'm
Under the
not able.
mods, multiplicative inverse is actually
This
modulo
is
inverse.
also okay. Okay, yeah, understood.
Yeah.
Because mod is being applied on both sides.
Yes. Yes.
Understood.
Yes. Yeah. This is what equivalent. It's both sides. Right. So basically, if you are not understanding this, you can actually bring it here and you can write it like a dot p minus 2 is basically 1 mod p. Right. So where this becomes actually x, and this can be compared with the model equation which we have, a is equals to 1
Right.
mod p. Right. Where x is a raised to the power p minus 2. Right. Take it slow. Please try to understand. You do not have to understand all the proofs, but right now at least convince yourself. Later, even if you forget the proofs, it's all right. But what you have to remember is x or a inverse is actually, this is what you have to remember ultimately. Okay, this is the final thing. Please remember this. You'll get this as a PDF. You'll have it. Right. You can go through it. This is also what you need to remember. Please. Right. Again, there won't be a very direct question like, okay, tell me what is p by q modulo m. No, there will be a very indirect question. Calculate this, report the answer in this. That's all they'll tell you. Then you have to understand what is that exactly. Right. So modular arithmetic is actually building block a lot of maths problems. Right. You will require it. And DP is just maths. Right. Now I'm hoping that all of you understood how this is obtained. Right. Now I will write the algorithm that I wrote for binary exponentiation under the modes now. Right. So bin power a comma b is res is 1. I am writing it in accordance to C++ constraints. Now, even if you do it in Python, of course, it's not going to give you a wrong answer, right? So I'm just trying to cover everything. Again, in Python, people like don't actually learn about in data type constraints because you don't have any, that I understand, right? But again, when it comes to very large counting problems, where the answer can, if you do not modulo, answer can go up to something like 10 raised to the power 100 or 1000 as well, right? There, if you don't know how to use modulo, right, then it will be a problem. I think you can understand that now, right? For smaller numbers, it was fine, right? But for really large numbers, no, it's not fine. Right, now we start. Now res we take it as 1. So while b in C++ you can just write while b, because as long as b is positive, it gives a true, right? So but for the sake of simplicity, I'll just write while b is not equal to 0. And if in, I think in Python you can write b and 1, and b and 1 actually checks for odd. This we'll talk about in on Wednesday, right? So while b modulo 2 is equal to 1, saying that this is an odd number, we will do res is equals to, what did I tell you? Res into 1l into a modulo mod, right? Now okay, now even for a you will do the same thing, a into 1ll into a modulo mod. B you don't need to worry about. Right. Now do you understand that everything is being handled? Again, in a lot of mod problems, there you will actually suffer initially. Okay, when you try to solve mod problems, you will suffer. You will have written exact correct algorithm in one go, but you are getting different answers. Why? Because you have not handled the mods. You are making some mistake in handling here and there. Right. That's possible. Right. So actually, modular arithmetic is Like it's a kind of frustrating topic. Okay, so even if you know the complete answer, if you are not able to handle the mods, you are not able, you won't be passing the question, right? It's pretty frustrating. Okay, so please understand it well. Understand where overflow occurs if you're using C++, right? If you're using Python, understand that you don't want the number to grow really big, right? You are modding it at places, right? Now when you're solving counting problems, there will be a lot of places that you are actually calculating the answer. Every single time you have to make sure that you are doing it under the mods, right? So okay, now again in the end you just return res, right? Can somebody tell me, is there a problem anywhere? Is this something, some corner case with respect to integer constraints again?
So what if b is like what if b is less than one or something? No, no, not one.
No, it won't. No, no. Let's just say b is greater than one, and sake of simplicity, let's just say a is greater than one. Every time a is less than one, you can just add mods, right? So, like you can do something like while a is less than zero, a is equals to a plus m, right? So this comes under the required range of 0 to n minus 1. Again, there is something that we are not handling. Check again. Res is all right.
Should we return res modulo m?
This is handled right here.
Oh, right.
Res
Okay.
is, yes, res is being modded. What I'm saying is, what if a is greater than, or a is in range of say 2 raised to the power 60 initially? Can you see that here it will overflow? On the first go it will overflow, right?
But
Here, hmm,
if that's the case, then it will already be overflowing, right? And
why?
even before that, because oh wait, yeah, we're passing them as long anyway.
Yeah,
Okay, man.
let's just say we're passing it as long. Yes. Actually, this won't be the problem in Python because this might take more time, right? But it won't at least overflow, and it will just take what 2 times more time, right? And it will bring it under the mods in the first option. But in C++, it will give you a wrong answer immediately.
So, but then how will you counter that then? Because long के ऊपर और क्या बढ़ा डाल सकते हो?
No, don't increase it. When you're passing bin pow, just pass it a modulo m. That's all.
Ah, all right. Okay.
Yeah. Mm, okay, but okay, this is not really confirmed. I'll confirm initially, but don't try to pass b modulo m as well. That might give you a wrong answer. Okay, I might have to work few examples and tell you, but don't do this. And remember that it's not you don't have to worry about b, to be honest, because the time complexity is log, right? Even if it was a square root or something, it was worrisome. With log, it makes no difference, because if it's 10 raised to the power 9, log 2 of 10 raised to the power 9 is something close to 30. If it's 10 raised to the power 18, it is something close to 60, 62. Right. So you don't really need to worry about it. Even if it's this, it's just taking what 30 more steps. Not a problem. Right. So do this, but let this remain this. Right. So this is how you handle it. This was just an example. When you solve problems, there might be different ways to handle it. Right. Now there might be some expression which require you to do a dot b plus c. Right. And before we talk about how you should do, whether you should add, multiply, whatever, but general rule of thumb, do all the multiplications first, right? Then do all the additions, right? Don't try to mix things up, right? Again, I'm not commenting whether it's wrong or right, right? Whether it is going to give you a wrong answer, right answer, but just for your simplicity, when you solve actually modulo problems, you will get frustrated, right? Because you won't even realize that somewhere you have not modded it and it's giving you a wrong answer. But I think, and hopefully in placements you don't get really hard mod questions, or where you have to apply a lot of mods, right? In DP you'll have to apply mods, but that's just one time where you are counting the DP, or where you are bringing in the DP recurrence relation, right? That's easy, but again, it's good to have a practice. So general rule of thumb, all the multiplications are solved first, then the additions, right? Just like BODMAS, right? Actually, even if you follow BODMAS, it's exactly same. Even with modulo, you can just follow BODMAS. Multiplications are modded first, then additions are done, right? And if it's a by D, so you need to solve this first, right? Here you have to solve this first, then whatever expression you get. So actually, it's nothing but a dot b plus c multiplied by d inverse, right? Basically, so a dot b plus c dot d raised to the power m minus 2 whole mod m, right? This is what you have to solve this, right? Sorry, m minus 2, right? Did I write m minus 1 here? No, that's fine, right? So I hope you understood this m minus 2 thing. Again, if you don't understand the proof, you don't need to remember the proof. Just remember this is this, the inverse is this, that's all. But to find this, you need bin power. So remember bin power as well, right? I will give you a link of CP algo. It has everything, right? Cool. 9:59. Just two more things and I'll close. So actually, how I use bin power, or not bin power, sorry, I use modulo is you don't have to do it. I do it for CP purposes, right? I have a whole class which handles modulo stuff. So basically, you can call it as a different data type. I call it mint, right? It's called mod int, right? And in C++ you can make templates, right? So I have templated it with what mod I need. So 10 raised to the power 9 plus 7. Uh, let's say this. Actually, I have already typed def to mint. So this is a mod int class. So mod int m, something like this, right? So m is basically integer data type. I can write it as m is equals to 7. I can write it as m is equals to m into 20, right? Or whatever I do, it will just use the mod. Every time I do this, it will do what I taught you, into 1ll, into 20, then whole mod. I don't have to do it explicitly. The class handles everything. Even for power, I can just use the power function, and it will do binary power. So it's embedded in the class, right? So that is just for simplicity again, right? I'm just telling you how to handle it, right? Again, you'll have to practice these problems, right? Once you get the hang of how to mod, where to mod, what to check, then it's not a problem, right? Now, one last thing, very small thing, we'll discuss how to calculate this efficiently, right? Now there might be some problems, and I okay, let's see if I'm able to find it. But these are one of the hard problems. I might or might not keep it, okay, but at least let's say just for understanding of modulo, let's actually know this, right? Now let's say you have to calculate a lot of these, right? You have to calculate a lot of different variations of these and add it to a number answer, right? Let's say the question is you'll be given lot of multiple nr, like n1 r1 n2 r2. You'll be given q queries, 10 raised to the power 6 queries of such type. What you have to do is you have to answer this. Answer is equals to n1 cr1 plus n2 cr2, right, plus n3 cr3, right, plus nq crq, right? Whatever be the number of queries, you have to answer this, let's say, right? But the fact that n is a given range, so n is basically less than 10 raised to the power 6, right? And you know that r is going to be less than n, equal to n anyway, right? So how do you calculate NCR? Now what is NCR? Let me expand it first. So it is n factorial, n minus r factorial, and r factorial, right? Basically. Now you can pre-compute the factorials first, right? Make an array called factorial. So let's say factorial of, or int factorial of length 10 raised to the power 6, right? And factorial of 0 is 1. Then all the consecutive factorials, I'm writing as a subscript, is equals to factorial of I minus 1 into I. Right, you can calculate this iteratively. Right, you get the factorial of every number, you store it. What is this called? This is called pre-computing. Right, you pre-compute the factorials. Now anytime you need the factorial, you have it there in constant time. One thing, this has to be done under mods. Okay, I forgot to tell you, you have to find this under a mod. So modulo some mod will be given, right? Because combinations are really huge. You have to do this under the mod. Again, how? Into 1ll, both multiplied, modulo mod. Right, you do it under the mods, you store it. Right, now how do you calculate it? I'll take a new page. Now n factorial, you can get it by factorial of n. Right, similarly others. Right, so basically this becomes factorial of n. I'm writing it as a subscript again. Factorial of n minus r, factorial of r. Right, how can you write this? Factorial of n into factorial of r to the power m minus 2 into factorial of n minus r to the power m minus 2. Remember that these are well below m. How? While calculating, we calculated another mods. Okay, so all these factorials are in the range 0 to m minus 1. Right, so obviously you have to do a bin pow here. Right, so the a thing, or this factorial of r, is in the range, so you don't have to worry about it, and this doesn't matter what the exponent is. Right, so you calculate this again for consecutive multiplications. Right, so you multiply this first under the mods, whatever you result you get x, you multiply it with this under the mods, and then you store it. Right, any doubts on this? I'm just using what I taught you earlier. Right, nothing new. Right, then you just add it again. While adding it, you need to do it under the mods. Right, how much time is going to take? Every single query is going to take log 2 of m time, and total is going to take O of q into log 2 of m. Right, so if q was 10 to the power 6 and m was 10 to the power 9, this is going to take 10 to the power 6 into 10 to the power 9 is roughly 32. So it's going to take 3 into 10 to the power 7, which is going to pass. Even in the worst, it will just take 1 to 3 seconds, which will pass. Right, so this was the question. This is how we solved it. Right, similarly there will be a question in your sheet which asks you to calculate a raised to the power b raised to the power c, and a, b and c are really huge numbers. I don't remember, I think 10 raised to the power 18 or 9 something. Right, so try to solve it. Right, okay, then that was all. Right, I'll give you the PDF for this. Any doubts, you can stay back, ask me. Right, any doubts until now, you can ask me right now. Otherwise you can leave. Thank you for joining the class.